Hello everyone again, in class and in cyberspace. We're going to talk about CoGraphs today and read once Boolean functions. The title is Read Once Functions Revisited, meaning that there'll be some newer things than appeared in the old-fashioned literature. And here we have a picture again of the view from Professor Rogers Matthews' office when he was in Haifa. So I'll talk about what read once functions are, some motivation. We will discuss CoGraphs and CoTrees, the graph of a Boolean formula, the property of normality, and some previous work on read once functions, and our method for recognizing read once functions and using the class of graphs called CoGraphs. Especially the notion of how to implement checking normality will be important, and some other results. So although you're used to talking graphs, I will start by first talking about an application called read once functions. A Boolean function that has a factored form in which each variable appears only once will be called a read once function. And as you can see in this example, we have here a formula, as you might have in logic or some satisfiability problem, AQ or ABP or ABD. Now this formula has A appearing 3 times, has B appearing twice, but we can pull out the A, pull out the B, and we have this equivalent logic form where every variable appears exactly once. That's the idea of a read once function, that you can factor it into a form where every variable appears exactly once. Why might you be interested in that? Well, imagine if you have a and/or circuit that implements this function. You only have one input for A, one input for B, etc. It goes into gates. You have no place where A has to be split into 2 different gates. Everything is unique. Here are some examples of some non-read once functions. If I had the formula AB or BC or CD, you can try, using pencil and paper, to factor that. You will not succeed in factoring it so that each one of those 4 letters appears only once. Similarly, AB, BC, AC, you will not succeed. If you try to pull out the A, you'll be stuck. You won't be able to get rid of the 2 C's, etc. Lastly, I'm assuming that these read once functions are assumed to be positive. That is, if I allow a variable to appear only once, well, if it appears in its negative form, I'll just rename it into its positive form. So if I have a not A, I'll just rename it to be A prime. And since it can only appear once, either as A or not A, I may assume without loss of generality that everything is positive. These are sometimes called monotonic functions. So our motivation for looking at this problem actually started by looking at a problem of how to factor general Boolean functions into a short form, a problem which is very important in circuit design, very well studied for 50 years, and it's very, very difficult. How to create a formula that is as short as possible for an arbitrary Boolean function. For read once functions, as a very special case, it's the case where, in fact, you can and you are able to, in very good order complexity, to squeeze that factored into the optimal form. The optimal form would be where everything appears once. So I'm looking at this read once function ball motivated by a larger problem to factor general functions. That general subject I'll talk about tomorrow. Today we'll formulate things about read once functions. Now to do this, I'm going to define the graph of a Boolean function. So each literal or variable of the function is assigned a vertex in a graph that is called the co-occurrence graph. So we have the vertices being a1 through an. These are the variables. And each prime implicant, sometimes called a minterm, sometimes called a cube, forms a clique in this graph, gamma, not necessarily maximal. Formally, I have an edge between AI and AJ if AI and AJ appear somewhere together in a prime implicant. They co-occur. Remember, we saw co-occurrence graphs a few lectures ago in a different context. So here's an example. If this was my formula, this is a sum of products form. You see in the first term, ACD occur together. So in my graph, ACD ought to be a triangle. ACD, they are a triangle. Similarly, AEF is a triangle, AEF. So each one of these terms is giving me some edges in this graph. This is the co-occurrence graph. Every prime implicant gave me a clique, not necessarily maximal. Notice, for example, here, no, don't notice for now. Now we'll put that to the side, and I want to introduce the family of CoGraphs, and then we will merge the two ideas together. A CoGraph is defined in this recursive manner. A single vertex is a CoGraph. The disjoint union of CoGraphs is a CoGraph. And the join of CoGraphs is a CoGraph. Join means that I take a bunch of CoGraphs and I add all of the edges between them. And I can record how I build this in a data structure called the CoTree. In this data structure, as we'll see in an example in a minute, the leaves of this CoTree will be labeled by the vertices themselves. The union operation, the disjoint union, will be a parent labeled 0, and the join operation will be a parent labeled 1. Here on the right is my CoGraph. Here is the CoTree. Let's look at the CoTree and see how we built this CoGraph. Well, here I have 3 independent vertices with a 0 node. That means I take the disjoint union of these 3 greens. Here are the 3 greens, and I take their disjoint union. That is the left side. I have 2 pink ones. I have a 0 above it, so that's also the disjoint union. And now, above that, I have a 1, meaning I take this subgraph and the other subgraph, and I join them with all possible edges between the 2 sides. Just this very shallow CoTree already gives you complete bipartite graphs. These are examples of CoTrees, but here are some others. Clearly, the complement of a CoGraph is also a CoGraph. Why? Because the complement can be obtained simply by taking the same CoTree, changing the labels, 1s to 0s, 0s to 1, and I will get the CoTree for the complement. The complement of a connected CoGraph is disconnected. That's a property. And 2 vertices of a CoGraph are adjacent if and only if their lowest common ancestor in the CoTree is labeled 1. This is a very easy way to take the CoTree and decide connectivity between a pair of edges or not. You just take them, go up your tree until you find the common parent, and at that common parent, you know whether they're connected or disconnected, depending on its label. 0, not connected, 1, connected. And I would say that the CoTree is a unique representation of the CoGraph up to isomorphism. I can certainly take a tree and move the branches around and around. It's the hierarchy that's important. And there are two views of how to view this. One is this recursive construction bottom up. I take vertices, I join them, I take disjoint unions, I join those, and I build it up till I get the final CoGraph. That is this recursive construction. Okay. Alternatively, I could view it as a recursive decomposition. If I had a CoTree, or if I had the graph, I would be taking the whole graph. I would look, how can I break it? If it's disconnected already, then each piece become a subgraph underneath a 0 node. And then I continue recursively. If it's connected, then I can look at the complement. It will be disjoint. It will have disjoint components. Each of those, again, I can look at as separate graphs, which I will have joined all together and continue building the CoTree by recursion. Now, we all know the term about looking for graphs that have forbidden subgraphs. A P4 free graph is a graph that has no induced P4. Here's a picture of P4. It's the path with 3 edges and 4 vertices. A graph that has no induced subgraph P4 is called P4. And there we have the definition. And lo and behold, P4 free graphs are equivalent to CoGraphs. CoGraphs defined through this decomposition. The P4 graphs defined by some local forbidden configuration. On the left, I have a CoGraph. Notice it has no P4. Its path of P4 is closed into a cycle. It has no induced P4. On the other hand, on the right, my 5 cycle has 5 different P4s. So it is not P4 free, and so it is not a CoGraph. And here is the very nice characterization theorem. A graph is a CoGraph if and only if it has a CoTree representation. That almost goes if and only if, because that's the way we build it and record how it's constructed. The equivalent condition P4 free is what I've just stated, but we haven't proven. And the last condition, every subset of vertices of size 1 or larger than 1, either the induced subgraph on that subset is disconnected, or its complement is disconnected. That's not at all clear why that should be an equivalent condition, but I think I would like to prove that. Yeah, so let's go to the pen and paper to prove this theorem. Okay, so the cameraman would look at my page. We'll see that the first condition was that G is a CoGraph. And I want to show that that implies that it's P4 free. Well, suppose it's a CoGraph. I have a CoTree representation for it. And suppose, to the contrary, there exists a P4 somewhere in the graph. Here's my graph on the right. Well, what is the node at the top of the CoTree? Well, what's its label? Either my graph G is disconnected. If it's disconnected, so it has a bunch of different connected components, the label is 0. And where would this P4 exist? Well, if these are connected components, it would have to exist inside one of those components. If I assume that by induction, smaller graphs satisfy the theorem, then it cannot, these are CoGraphs, it cannot live in a smaller by induction. That handles the disconnected case. For the case for G connected, it's a CoGraph. The label here would be 1. That means that I have CoGraphs that are completely joined to each other. Well, again, where is my P4? P4 looks something like this. On the A, B, C, D. A and C are not connected. So that means that A and C cannot be in different components, right? A and C would have to live in the same component because they're a non-edge. Similarly, A and D is a non-edge. So A and D cannot be over here in one of these other components since it's a non-edge. So D is also not here. It must be together with A and C. Where is B? Where is B? Well, on the one hand, it's disjoint from D. So it cannot be in one of these outer suburbs. So it must be here inside the same component. Now, A, B, and C, D are all in the same component. That would give me a P4 inside one of the components. This is a smaller CoGraph. That's a contradiction to the induction hypothesis. So we've proved that the implication CoGraph implies P4 free is true. Now let's go on to the next implication. Suppose the graph is P4 free. I want to prove that this last condition holds. That is, that for every x that is size at least 2 vertices or larger, either the induced subgraph is a connected component in C, you would say that it's in G, so you would say that this is either G connected or, sorry, wrong. It's either G disconnected, or G bar disconnected. Well, suppose not. Suppose that I did have x which is connected in both G and G bar. Okay, so my picture might be something like this. In G, the picture looks like this. X is connected in G and in G bar. If it's a clique, I'm done. Because if this was a clique, then its complement would be an independent set. That's certainly not connected. So there must be some non-edge in this let's call it AB, a non-edge. Well, but this is connected, so there's a path between A and B. Let's take a shortest path. If that shortest path was, say, hop, 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 I'd have a P4. So I can't go hop, 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 hop. I can only go hop, hop. So there's some Y that sees both A and B. Great. Now, what's going on in G bar in the meantime? In G bar, A and B are connected. And they are disjoint from Y. But G bar, X in G bar, is also connected. So there must be some way to get from A to Y. Again, if I were to go from A to Y with a hop, 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 I would find a P4 here. The complement of a P4 is a P4. So I must have a Z that sees both A and Y. So I have this, this, and this. And these is an edge. What's happening between B and Z? Well, if it's a non-edge, I have a P4. So it must be connected. Now this is my state of the art in G complement. Let's go back and see what's happening over in G's neighborhood. Well, we still have A and B, and we still have Y, and now we have Z, and Z is connected to all three of them here, so it's disconnected to all of them here. Well, let's keep playing the game. Z and Y are not connected, so there must be something that connects them. It has to be a common vertex. It can't be hop, hop, hop. So there must be a Y prime that sees both of them. And now, hop, 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 no edge, no edge. So A and Y prime better be connected, otherwise I would have a P4. So this is connected. Similarly, down here, what about B to Y prime? Well, if that was missing, then I would have a different P4. So it is also connected. Now what's going on downstairs? Well, you can guess. I have this, I have this, this, not dot, 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 this, and now I have a new vertex Y prime, which is dot, dot, dot. This is disconnected, this is disconnected, this is disconnected, this is disconnected, and now I take him and maybe here. There must be a Z prime that sees both of those. And so forth. This will be connected, this will be disconnected, and so on. And what I'm doing is I'm growing this iteration after iteration after iteration. Okay? This construction keeps going on forever. But I'm running out of vertices. X is finite. So I'll get stuck. It can't happen that you can go on forever with a finite set. So this will eventually stop. Eventually, I won't be able to continue any further. And that will be my contradiction for the supposition that there is such an X. Therefore, there isn't. Now let's look at the last implication, which is very easy. We assume that for every X, either it's disconnected in G or it's disconnected in G bar. And I want to show that that implies that I can construct a CoTree, that it's a CoGraph, and I can construct a CoTree. Well, that's really simple. It's exactly what this was designed to do. If take all of the vertices. We'll do this by induction too. Take all the vertices. Well, they form an X. If it is disconnected, well, if it's disconnected, I have separate components. Great. Now I can assume that the theorem is true for each component. Therefore, each of these is a CoGraph, and therefore the disjoint union is a CoGraph. I'm done. If it is connected, well, then its complement is disconnected. In the complement, that also partitions the vertices into pieces. The only difference is now, though in the complement, I have these pieces. So in the graph itself, I have them all joined together. So again, I work on each one separately by recursion. They are CoGraphs. The join of CoGraphs is CoGraphs, and I'm done. So that's the proof of the theorem. Now we can go back to the slides. So I've proved this very nice theorem characterizing CoGraphs. How do we recognize a CoGraph? Well, I think that we've just sort of seen it, and I'll just go through these steps which repeat the construction I just did. The naive algorithm would simply be to construct the CoTree. If the graph is disconnected, make a label root 0, and continue recursively on each component. If it's connected, make a label rooted 1, look at the complement. If the complement is connected, then fail. Otherwise, I partition the vertices, and I can continue recursively. The complexity of this naive algorithm would be n to the third power, n cubed. But over time, there have been linear time algorithms found by Derek Corneal and various friends of his. In fact, the name CoGraph stands for complement reducible graph, since it can be decomposed by using this naive algorithm. The name was actually coined by a student of Derek's named Lerks, Helmut Lerks, in a tech report that he wrote at the University of Toronto in 1971. Lorna Stewart worked on the problem in the late 70s, and by, I think it was 81, 82, they published their major paper on CoGraphs. So here we have just another example. If this is my graph, how do I decompose it? It's connected, so I start with the root labeled 1. I look at its complement, partitions it into 2 pieces. I create subtrees for those pieces with zeros. Then I look at that subtree. It partitions into these pieces. Here's my CoTree so far. Then I look at this part. It builds this part of the CoTree, and continuing right along, adding CD, I'm growing my CoTree just by decomposing. And this ends up being the CoTree for the original graph. And there it is in another view. And notice here that my label zeros turned into stars. No, my label zeros, turned into, my label zeros turned into pluses, and my label ones turned into stars. And there's a reason for that. And that's going to be the connection with the functions, the read ones functions. So recall that a co-occurrence graph we formed from a Boolean function where each prime implicant or term gave us a complete subgraph in this graph. And we recall this example, and here was our graph, which happens to be the graph that we just worked on. This is the co-occurrence graph for this formula. So this was taking a function and creating a graph for it. Now let's look at how to take a graph and create a function for it. Let's take an arbitrary graph. For each maximal clique in the graph, I want to create a prime implicate of a new function called the function of the graph. Here's an example. This graph has a triangle here, CEF, that gives me this term. A triangle here, ABC, gives me this term. An edge, AD, an edge, CF, DF, gives me this formula. So here I take a graph and I build a function. Now, you might say, but you're using maximal cliques. We know that it's hard to find all the maximal cliques of a graph. That's true. But we're only going to end up doing it for CoGraphs. And that's going to be simple. I must introduce one other notion about normality. A function is normal if this process of taking the function, mapping it to its co-occurrence graph, and then taking the co-occurrence graph and mapping it back to a function yields the original function that you have. If it does, this two-step process gives you the same thing. We call it a normal function. So f is normal if and only if the cliques of the graph are precisely the prime implicants of the original. Here's an example. If f1 was ABC, the function ABC, it would give me the triangle as its co-occurrence graph. If my function was AB plus AC plus BC, it would also give me the same triangle as its co-occurrence graph. Going the opposite direction, however, the triangle gives me function number 1. So number 1, ABC, is normal. AB plus AC plus BC is abnormal. Now we come to Gurvich's theorem. Let f be a positive function and let gamma be the graph of f, then the following statements are equivalent. f1 is a read once function. It has a factored form where every variable appears once. If and only if it is a normal function and its graph contains no subgraph isomorphic to P4. Look at that. It's giving me two conditions that characterize together read once functions. The graph has to be a CoGraph. The function has to be normal. Other conditions that are equivalent that we won't go into as deeply, the graph and the graph of its dual function are complementary. And another one, for all prime implicants of the function and all prime implicants of the dual of that function, the cardinality has to be equal to 1. I just give you those results, but you will have to read up on that if you're interested in following up. Both of those conditions are important and required. Here's a function whose you can easily see its co-occurrence graph is the chordless 5 cycle. It is normal, but its graph is not a CoGraph. C5 has a P4, but this is normal. On the other hand, its dual happens to be this function, and its co-occurrence graph is the complete graph on 5 vertices. It is not normal, but its graph is a CoGraph. So both of these normality and CoGraph conditions are required. So the proposed method for recognizing read once functions is simply this. You take an input in sum of products or product of some form, either way, it doesn't matter. In computer science, we would say DNF or CNF. We test to make sure it's unary. We build the co-occurrence graph. We run a CoGraph recognition algorithm, like an efficient one of Cornel's, or a slow one, like the naive. That gives us a CoTree and the function f of the graph. Of course, if it failed to be CoGraph, we quit and go home. If we succeed, we continue, we check normality. If it's not normal, we quit and go home. Otherwise, we declare it's read once, and the CoTree actually gives you the factored form. What is the complexity of this? Well, use of Gurvich's theorem and CoGraph recognition, together with checking normality in polynomial time, will end up giving us an algorithm whose complexity is on the order of L, the length of the input formula size, times n, the number of variables in the function. So it is polynomial time algorithm based on the product of how long the input is times the number of variables. Let me just say something about the previous work on this problem. In 1975, you have the first paper on this, and 20 years later, another paper on it. I don't think that Pear and Pinter knew about Hayes in the first place, but they have different techniques, and both of them give algorithms which are exponential in complexity. There was additional work on them done in the theoretical mathematical side, those characterizations. The work by Gurvich was done in the early 80s, but it was only published in English in the 1990s, 1991. Another paper, totally independent, not knowing about Gurvich's work, gave the same theorem in 93. Another work in the that did know about these, or at least some of it, from computer learning theory, uses this characterization in trying to learn read-once functions. So here was our algorithm. First, we check that it's positive or unate. We build the co-occurrence graph, test if it's a CoTree, then test normality. But how do we do it efficiently? Well, the camel is supposed to indicate an efficient water usage machine. How about an efficient computer machine? So for the CoGraph recognition, we would use either one of Cornel's algorithms or the naive algorithm. Okay, and that we know how to do. It's checking normality that we don't know how to do. Well, I know how to do it. I'm going to tell you how to do it. The way we'll do it is to compare the input representation, it's the sum of products or product of sum, and the generated function that we get from the CoTree, the parse tree. Okay. On the one hand, we have the expanded form. On the other hand, we have the factored form. We need to decide whether the cliques of the graph of this function equal the prime implicants of the original. So here is how we're going to do it. First, let's look at the original function and the prime implicants of that. Okay? We're going to make a bit matrix, which will simply be the characteristic vectors of each prime implicant. So imagine, for example, I have this bit matrix. It's zeros and ones. I'm going to have my variables v1, v2, up to vn, and I'm going to have prime implicate 1, prime implicate 2. These are just the terms of your DNF. And I'm just going to have 1s when it's in it and 0s when it's not. The usual characteristic vector. Okay, and here are my list of prime implicants, and I've just given the characteristic vector for for its set of variables. We'll call that P. What I'd like to do now is, and I have to show you how to do that, build another matrix similarly, V1 out to Vn, where these will be the max cliques. The maximal cliques of the graph. I guess I was using gamma that I get from the from my factored form of the CoGraph. Okay, so, and here I will also have characteristic vectors for each clique. And then I'll just compare, are they the same? Are the prime implicants the same as the max cliques? This is easy to build. This, I have to show you how to build them. So what do I have with me? I have my CoTree, and from that I want to find all of the maximal cliques of the CoTree, of the CoGraph. Okay. It's better for me to do it on an example. Okay, here's my example. Here's a CoTree. It represents the factored form at the bottom of the slide. What are its maximal cliques? So here is how I'm going to do it. And I will try to explain what's on this slide, and if I can explain that correctly, you'll understand perfectly what the algorithm is. So let's look at this. I have variables A, B, C, D, E, F, and G. I'll say that A is vertex 1, and I'm going to write that in binary. 0, 0, 0, 0, 0, 0, 1. B is 0, 0, 0, 0, 0, 1, 0, etc. Down to G, which is 1, 0, 0, 0, 0, 0, 0. This is the characteristic vector of each of these singletons. And sometimes I will call A 1, and sometimes I'll call this 2, and C I'll call 4, and D I'll call 8, and G I'll call 64. Because sometimes I like to look at this in binary when I'm looking at the characteristic vector, and sometimes I look at it in base 10, which is more familiar to me. This is the numbering of the singletons. Now, what happens on my, back to my CoTree on the slides, what happens when I take A and B? singleton A, singleton B, and take their disjoint union. Well, they are individual vertices. The disjoint union is two cliques, a one-point clique and another one-point clique. And so I record that as the list, the clique consisting of 1, which is A, and the clique consisting of 2, which is B. On the other hand, if I take over here on the right, let's say, the join of a single vertex E, a single vertex F, I get an edge EF, that is a single clique, and I'm listed here as the single clique 48. Why 48? Because this was 16, this was 32, this is meaning bit number 5 was lit, whoops, bit number 6 was lit, here bit number 5 and 6 are lit. So 48 is simply the binary string consisting of the set EF. That's a clique. Same over here. I take the disjoint union, sorry, I took the join, and I get the clique consisting of CD, the edge CD, which is denoted in the characteristic vector as 12, meaning bit number 3 and bit number 4. More interesting is here. What happens if I take this clique, and this clique, and take their disjoint union? Well, I have 3 separate cliques. So I have a list of them. I have clique consisting of CD, encoded as 12, G alone, encoded as 64, and B and EF as 48. And now finally, if you're with me so far, here I have the disjoint union of 3 cliques. Here I have the disjoint union of 2 cliques. If I want to take the join of those, okay, so what am I doing? I'm taking these 2 cliques, this clique as one side. This was A and B. I'm taking this clique, and this clique, and this clique, which are CD, G, and EF on the other side. Now I'm taking their join. What are the cliques of the join? Well, cliques of the join will be 1 from the right and 1 from the left. So this and this will be a clique, A and G, A and the other 2. So here I have a clique, here I have a clique, here I have a clique, and same here. I have 6 cliques. And what are those 6 cliques? It's the cross product of these 2. So we have 1 and 12, which is 13, 1 and 64, which is 65, 1 and 48 is 49, 2 and notice I'm doing these in bit operations. So what looks like addition is really just union of the bit vectors. And similarly, 2 crossed with these give me these. So now I have 6 cliques here, and here they are. What did I have in my original formula here? Well, I could calculate them the same way. And lo and behold, I have the same 6 cliques. The cliques of the CoGraph in this example are the same as the prime implicants of my original. Okay. Where am I? Okay. So what do I have? I have the bit vector for the prime implicants. I have the bit vector, or the bit matrix for the CoGraph max cliques. I sort them lexicographically. I now compare them. Either the same or they're different. Of course, I could cut this situation if the size of the matrices was different. I wouldn't even have to compare. But if they're the same size, I do have to compare. Okay. So that is the way that we were able to check normality. And the bottom line complexity is dominated by normality, which is the length of the input times n. We did some experimental results on some on our method versus some standard library packages on factoring Boolean functions and how they performed. And you can see some of these are very big functions. The ones that are in the libraries generally ran more time than ours. Both gave correct solutions. Okay, so my conclusion is that here we have both an interesting theory of CoGraphs and how it was used in this real computer science, electrical engineering application. Okay. So now I'd just like to conclude with one more remark. And that is, you'll recall from the last lecture, I said that CoGraphs, which you now know what they are, would be a subfamily of permutation, which we learned last week, and which itself had the property that they are TRO and the complements are TRO. How do we know that CoGraphs are permutation graphs? Well, I didn't talk at all about transitive orientations. But let's just see the immediate observation of why CoGraphs are permutation graphs. And I'll show that very simply. CoGraphs have this nice form of a CoTree in decomposition. So a CoGraph, remember, I'll do this by induction, looks either as disjoint CoGraphs. If that's the case, I take a TRO here, TRO in each piece, combine them, I have a TRO of the whole graph. So CoGraph is TRO in this case. If, on the other hand, my CoGraph was connected, it would be of this form, the join of CoGraphs. Well, that's also very simple. Take a transitive orientation of each piece, and now just make all edges go just like you would orient a clique. And that gives you an orientation of the whole graph. So what I've showed is that a CoGraph, either case, is TRO. But the complement of a CoGraph, being P4 free, is exactly a CoGraph. They are self-complementary. And so if the CoGraph is TRO and the complement is TRO, so it's co-TRO, so this graph is both TRO and co-TRO, and so it falls within permutation graphs. That's a kind of fast proof of that. Okay, so next time I'll show you how this read-once algorithm fits into the larger computer science question of factoring Boolean functions. And we'll also talk a little bit more graph theory. So that's it for my portion of today's lecture. And I'll see you tomorrow. But stay tuned. We have a student who's going to give a presentation coming right up.